Hello everyone, welcome to this online class. Today we are going to look at applications of first order ordinary differential equations, and in particular we're going to look at the electrical RL circuits. So I want us to consider this series circuit, the one that you have drawn here, which consists of the resistor R here denotes resistor, L denotes the inductor, and the E denotes the electromotive force, EMF, to mean electromotive force, e.g. battery or generator. So that is a series circuit. It consists of EMF, resistor, and inductor, as you can see from the diagram. Now the EMF means electromotive force, produces a flow of current in a closed circuit, and the current produces a voltage drop across each resistor and inductor. Now, there are some laws that we are going to apply to be able to come up with the ODEs governing the flow of current in this series circuit. The first law is what we call the Faraday's law. I'm going to state it. Faraday's law. Faraday's law. Now, what does it state? It simply states that the voltage drop across the inductance is given by, I can write in full that the voltage drop across the inductor is given by that voltage drop. It is equals to denoted by E subscript L, and is given by L times di dt. What I'm using as I here denotes the current in the circuit. Current in the circuit. It is a function of time t. Even the EMF is a function of time t. This one is also a function of t, but the others are constant. These are constant. Even this other one is a constant. Now that is Faraday's law, that if you want to know the voltage drop across an inductor, then it is given by the inductance times the derivative of current with respect to time, rate of change of current. Another law is Ohm's law. So you write number 2 is Ohm's law. Let us state the Ohm's law. It states that the voltage drop across the resistor, let me write the voltage drop across the resistor. The resistor is R capital, is given by let's denote that by E subscript R to mean the voltage drop across the resistor, and it is the product of the resistor and the current, R times I. Remember, I is a function of T. where T denotes time. Now, we have those two laws governing the voltage drop across resistor and also the inductor. And I will also say that the I denotes the current in the RL circuit. E denotes the impressed voltage or electric potential, or what we are calling the EMF. It is also a function of time T. Now, I want to know the voltage because you see, our EMF is E. Now, that voltage that we started with, some of it will be dropped at the resistor, some of it will be dropped at the inductor, and some of it will be used to produce the current. So there's a law that governs the voltage in the series circuit. That law is what you're calling the Kirchhoff's voltage law. So what does it state? We can write Kirchhoff's that's double H, Kirchhoff's and double F. Kirchhoff's voltage law. Kirchhoff is just the name of somebody who came up with this law. It states that the sum of the voltage drops the sum of the voltage drops across the resistor and inductor in an RL series circuit. RL series circuit is equals to the total EMF is equal to the total EMF. EMF is electromotive force or the impressed voltage. Total EMF in a closed circuit. In a closed circuit. So what it simply means is that when I add the voltage drop across the resistor and that across the inductor, that will give us the electromotive force. So you can write IE E subscript L plus E subscript R should give us E. And we know E subscript L is given by the Faraday's law. And write or E subscript L was L times di dt. E subscript R, we got R times I is equals to the EMF, which was E, or the impressed voltage. Now this is an ODE that governs the flow of current in the circuit. So you can comment on it and write that this is the ODE governing the flow of current in the RL series circuit. So what we said is that R and L, these are constants. While I and T are function, I and E, these are functions of time T. Functions of time T. So that is a first order ODE. It is linear. This equation is linear. In the dependent variable I. And so you can solve it using the integrating factor method. Now, let me give you an example of a question that deals with RL series circuit. You can write example. So here, you write this. Let's call it example 1. So I'll delete this and call it example number 1. We are going to write the question on that example number 1. This is the question. So we are given this question that a series circuit has an EMF given by E is equals to 100 sine 40t volts, a resistor of 10 ohms, and an inductor of 0.5 Henry. If the initial current is 0, find the current at any time t. So, of course, we know the ODE governing the flow of current in the circuit. So we'll write the ODE, but before that, let's see what you have been given. So you just analyze this. You can write given that our E is equals to 100 sine 40t. That's a function of time. We are given the resistance to be equal to 10, and the inductance is equals to 0.5. Also, we are told that the current, the initial current, when time is 0, the current is 0. That's what we have. That's an initial condition. So this one, I can comment on this and write this as an initial condition that you need to apply. Initial condition. We will apply that to get the arbitrary constants. So now the governing equation, or the ODE governing the flow of current in the RL circuit, is given by L times di dt plus Ri is equals to the EMF. If I substitute those values, I am going to get 0.5 times di dt. Our R is 10, so 10I. Our EMF is 100 sine 40t. Now you need to make the coefficient of the highest derivative to be 1. So this means that if I divide through by 0.5, I'm going to get di dt. You see, dividing by 0.5 is the same as multiplying by 2. So this will give us 20I, which is equals to 200 sine 40t. Now, this equation is linear in the variable, the dependent variable I, where I denotes the current in the RL series circuit. So this is a linear ODE in the dependent variable. I. Of course, our independent variable is T. So from this equation, the coefficient of I is a function of time. This is what you're calling P of T. So I can now integrate it, the integral of P of T dt. That should be equal to the integral of 20 dt, which is simply equal to 20t. So now we need to find the integrating factor. It is defined by the exponential of the integral of P of T dt, which is the same as exponential 20t. So now let's multiply the ODE by the integrating factor. This equation, let's call it star. So now the next thing is to multiply equation star by the integrating factor. What are we going to get? It will be exponential 20t times the I dt plus 20 exponential 20t times I is equals to 200 exponential 20t times sine of 40t. So that's what we have. And you need to know that once you have multiplied a linear ODE by an integrating factor, the left-hand side reduces to the derivative with respect to the independent variable, in this case it is t, of the product of dependent variable, in this case it is I, and the integrating factor, which is exponential 20t. This should be able to give us 200 exponential 20t times sine of 40t. Or if I multiply by dt on both sides and then integrate, we are going to have derivative of I exponential 20t is equals to 200 exponential 20t times sine of 40t dt. So now you integrate both sides, integrate this and also that. So now you're going to write a constant of integration. Remember, when finding the integrating factor, you don't write the constant of integration. So on the left-hand side, this is integral, this is derivative. Those are inverses of each other. So they'll cancel out so that we have on the left, we'll simply remain with I times exponential 20t is equals to. Now, how do you integrate this? Let this one is a sine, that is trigonometric. The other one is exponential. So this one is exponential. You could factor out the 200 or you could pick it together with the exponential function. So I'm going to use integration by parts. Let u be equal to, which one comes first? We are going to use LaTeX. We encounter t before e, so let u be equal to sine, that space is very small. That's not enough. So you're going to say let u be equal to sine 40t, and the rest will form dv. That is 200 exponential 20t dt. So now I need du. This means that du is the same as 40 cos 40t dt. And v, integrate 200 exponential 20t, that will give us 10 exponential 20t. So that when you use the parts formula, I expect this to be uv minus the integral of v du. And when you substitute our u times v, that is 10 exponential 20t times sine 40t. That's uv minus the integral of v du. Our v is 10 and our du is, our v is the whole of this 10 times the exponential function. We are multiplying by this, so that will be 400 exponential 20t, then there's cosine of 40t dt. Again, I need to use another integration by parts. So again, we are going to say let u, in this case our u will be equal to cosine of 40t, and the rest will form dv. dv is equals to 400 exponential 20t. So what do we get? You need to differentiate u. This means that du is negative 40 sine 40t dt. Integrate dv to get v is equals to 20 exponential 20t. So when I again substitute it into the parts formula, we are going to get 10 exponential 20t sine of 40t minus, now the parts formula should apply in that integral. So u times v minus uv minus the integral of v du. Let me replace the values of u and v and even du. So this is the same as 10 exponential 20t times sine of 40t. Now minus u times v, if I open the bracket, it becomes a minus. U times v, that will be 20 exponential 20t cos 40t. Now here we will have plus v du. So it's a plus. Now v times du again, that's a minus. So here we'll have another minus. And that is 800. Of course, it is the integral, I mean. 800 exponential 20t sine 40t dt. How else can this be written? This can be written as, look at the integral we started with. It was the integral of 200 exponential 20t times sine 40t. That's what we had on the right-hand side. And on the left-hand side, that was I exponential 20t. So this thing can be written as 10 sine 40t minus 20 cos 40t times exponential 20t, because it is common, then minus 800 is the same as 200 times 4. So this is minus 4 times the integral of 200 exponential 20t sine 40t dt. But now the question is, what is this integral equal to? That is the question. Look at, it is the same as the one we started with. It is the same as the whole of this integral. Let me bracket it. The same as this. And what was it equal to? On the right-hand side, we got I exponential 20t, because the others cancelled, integral and derivative cancelled, so that we got the same thing on the left-hand side. So where we have that integral, we are going to replace by I exponential 20t. So instead of this, it's the same as I exponential 20t. It's the one that we started with. And on the left, we still have I exponential 20t. Take note, it is the same I that we had on the left-hand side. So now I need to collect like terms. So I need to take this to the left-hand side. Take this to the left-hand side so that it becomes plus 4, because on the right it is minus 4. When you take it to the left, it becomes plus 4. So you say, or I exponential 20t plus 4I exponential 20t is the same as 10 sine 40t minus 20 cos 40t, and this is times exponential 20t. Remember, there's a constant c of integration which I've not written, so I need to add a constant c. I'll add it, so you can just say plus c plus a constant c of integration. Don't forget to add the constant of integration. Once you're through with the integration part, then you add the constant c. Now, on the left, that will be 5i, you write or 5i exponential 20t is equals to what you have on the right-hand side. That is 10 exponential, no, there's no exponential, 10 sine 40t minus 20 cosine of 40t. This is multiplying exponential 20t, then plus a constant c. So if I divide through by 5 exponential 20t, we are going to get this. I is equals to 2 sine 40t minus 4 cos 40t then plus c over 5 exponential negative 20 t. C over 5 is another constant. You can call it C1. So instead of writing C over 5, you just another arbitrary constant, call it C1. So this is the general solution. So therefore, we now have I is equals to 2 sine 40t minus 4 cosine of 40t plus a constant C1 exponential negative 20t. So what we have here is our general solution. So let's comment on it. You write this the general solution. Now we need to find the particular solution. What were we told? That the current is 0 when the time is 0. So let's apply that. So apply, let me use another color. Apply this condition. Apply this I0 is equals to 0. That this means put t is equals to 0 and I is also equals to 0. When you substitute, what do we get? We are going to get 0 is equals to, remember where we have sine 0, that is 0. Cosine 0 is equals to 1. So that is 2 sine 0 minus 4 cos 0 plus a constant C1 times exponential 0. So this simply means that 0 is equals to, because this will be 0, so we'll have negative 4 plus C1. So therefore, you can make C1 the subject. Therefore, C1 is equals to 4. That was the constant. Now we know its value. So when you replace back to the general solution, you get the particular solution. So hence, let's replace C1. You write here hence. Now we can talk of our current I being equal to 2 sine 40t minus 4 cos 40t, then plus 4 exponential negative 20t. What we have found here is the particular solution. It is the current as a function of time. So this one here is the particular solution. It gives us the current in the circuit at any time t. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems in applications of first order ODEs. Bye-bye.